Calculate the mass defect and reaction energy of the reaction above, given the information in the table. State whether the reaction is exothermic or endothermic. The mass defect, delta M, is a difference in mass between the reactants. So those are all positive signs, okay? It's kind of like, this time it's backwards from what we normally do, right? Normally it's final minus initial whenever we do energy problems or kinematics or stuff like that. This time, it's the mass of the reactants, which are positive, and we subtract away the mass of the products, which is the final situation we have. So it's the mass of magnesium plus helium minus the mass of silicon plus the mass of the neutron. We use our table. Okay, here's the mass of magnesium. Here's the mass of helium. Remember, this includes their electrons. Here's the mass of silicon. And here's the mass of the neutron. We do the math, and we get a mass defect of 0.002811 atomic mass units. The positive mass defect shows that the reactants have more mass than the products. The mass defect needs to be in different units to solve for the reaction energy. So let's convert the mass defect to MeV per c squared like a nuclear physicist would. So here's our atomic mass units. Here's a conversion of MeV c squared, 931.5 MeV per c squared equals 1 atomic mass unit. And we get a mass defect of 2.61845 MeV per c squared. The reaction energy Q is delta mc squared. So here's our mass defect in units of MeV per c squared. You multiply that by c squared, well, what happens is you cancel out the c squareds. And we'll round it here and we get 2.62 MeV. The reaction energy has the same sign as the mass defect. When Q is positive, the reaction is exothermic. Energy is released during the reaction. The energy released comes from the change in mass. The reaction here is exothermic. The mass is some of the mass is being converted into energy.